This lesson will be about the interference and the double-slit experiment, how that goes. I've also talked about this in part 6 of the video as well, and some information about part 6 and part 5 is also carried over to this lesson, but I will be going through that briefly as well, so that anyone who's coming towards this video for the first time can easily understand what we're going to talk about. So first, we need to understand what is interference and coherence. Interference will be meeting of two waves in a medium, and the result of them will be caused, or you can say it will be because of the superposition, right? And coherence means that whatever waves are actually interfering, they need to have, they need to be of the same type. For example, sound with sound, light with light, water with water. There needs to be no phase difference between them. Sorry, there needs to be a constant phase difference between them. There needs to be a constant phase difference. This means that the angle between them should always remain constant, like this one. So there are two waves and there is an angle between them, as shown on the unit circle on the left. The angle between the waves should be constant, should not be changing, and that can be found by using this time as delta t with this time, which is actually the time of one complete wave. Let's call this t, and this t can be chosen from any wave, either the purple one or either the green one. The formula becomes delta t by t multiplied by 360 if you're calculating in degrees, or by pi if you're calculating that in radians. So these two conditions need to be met for coherence, or you can say this is what coherence means. The second part is going to be dealing with demonstrating two-source interference in water using sound, light, and microwaves. So you must be familiar with this. So what happens when you do this interference? Now, when this two-source interference actually plays about, first we see what a single source is going to look like. So there are going to be circular wavefronts because of the single source. Okay. Now, please be advised that first step towards this idea is basically this understanding and acceptance that first the light waves are actually diffracting. The light waves are diffracting, which means that when the light wave passes through this narrow gap, it actually bends to become a circular wavefront or have a circular wavefront. This is the first thing that we need to accept. Once we do that, then we can move towards this idea that one source is producing circular wavefronts, and when the second source, which also produces circular wavefronts, comes into play or comes up into this scenario, this is the pattern that you're going to see on the screen. This is done with water waves to make it simple to at least observe, but this is also observed by light waves, which we can't see with eyes, but we can see its response on the screen, how light behaves. Now over here, the second thing that we need to understand is that the interference is occurring over here, how that interference is happening, because we have two sources. So we use a single source, for example, we use a single source and deliberately convert that into circular wavefront so that this actually acts like two sources. So this is source 1, this is source 2, although it is coming from a single light source. The light source or the bulb or the laser that we're using is single. We are deliberately converting it into two parts so that they remain coherent and they remain monochromatic, and the chances of interference can increase. This is about the double-slit experiment, and this is about the interference pattern of two sources. So when this happens, that when the conditions are met, and what are those conditions? That they need to interfere, they need to be the same type, and they need to be coherent. When those conditions are met, the two sources will produce an interference pattern on the screen that can be observed. If it is with water and light, it can be observed. If it is with sound and microwave, it can be measured with mic and the CRO. Okay, you can pause the video to see what the coherence actually means at this point, but that's already covered in a previous video. Okay, so we are talking about this. Okay, now the main goal of this whole exercise, of this whole idea, was to measure the wavelength of light. We didn't know at the time how to measure this. So what we've done is divide this diffraction experiment or the double-slit experiment that actually looks like this. Two sources creating wave pattern. So what happened in this experiment and what was the target? So what they set out to do was they used a single light source, bulb at the time, and they provided two apertures in front of the light source. Okay, so light source actually became or started having circular wavefronts like this. Now, when you observe clearly, when you observe closely, you will realize that these circular wavefronts are actually interfering at certain points on the wave. And how is that happening? Let's look at this. So you can see that this one single point is actually an interference of crests of both waves. So this will be a constructive interference. Now let's visualize this from the side. If it had been a wave viewed from the side, so what's happening? So this is the crest, this is trough, this is crest, and this is trough, and so on. Similarly, from this side, we are having a crest for the red wave, and on this side, we have a crest of the blue wave. So they are meeting at this point, and crest plus crest creates constructive interference, and even trough plus trough creates constructive interference. Wherever there is a difference of phase, wherever one has a crest and one has a trough, we will see a destructive interference, right? Now, let's let this animation play out. Let's see what this animation is actually going to look like with reference to light. So we placed a screen in front of them. What the scientists were expecting, what were they looking for? They thought, and a common observation should also give us the same answer, that if we have two holes, they should only see light actually exactly in front of this point. They should only see the light exactly at this point, just like shadows, just like light coming from a pipe hole. Okay, but what they saw was peculiar at the time, because this is not what they were expecting. What they saw was a pattern of bright and dark fringes. Bright and dark fringes. Now this was, you can say this was strange at the time, because this should not have happened. But if this is happening at the time, what they argued, what they discussed was that it is only possible that if these parallel wavefronts have somehow become circular. And if they have become circular, then at certain points in time, there will be constructive interference, and at certain points, there will be destructive interference. Now, it's not possible to draw that over here accurately. Let me show you an animation for this. So this is how that's going to happen. So we have two sources, one at this point, one at this point. We're going to let this play out. So please be advised that we are actually copying the same idea, that this is one source of wavefront, this is source 1, and this is source 2. Now let's see what happens. Okay, let this play out. So again, circular wavefronts are being generated, and how do we have the guarantee for this? We have the guarantee for this from the concept of diffraction, because if parallel wavefronts are coming, they're going to become circular. That is why this is what we get on the output of the holes that we have added, the two openings. So let this play out. Now observe how these wavefronts are actually interacting with each other. Now, the moment they reach the screen, before they do that, I'm going to pause the video and I'm going to show something. So what's happening in this region? You can see that this is a bright color, or this is actually a colored region, and it is followed by a dark region. So this is the dark fringe, this is the bright fringe. To put it into plain perspective, this one is bright because it is experiencing constructive interference. And this region is dark because it is experiencing destructive interference. And so on, then constructive, then destructive, then constructive, then destructive. And we can see that over here as well in the waves, that two crests are actually meeting together to make a constructive interference. And over here, two troughs are actually meeting to make constructive interference. Notice that constructive interference is actually addition of both crest and trough. It doesn't matter. Okay. So, but if we observe for the dark band, if we just draw a line for that, let me erase this. So if we draw a line for the destructive interference, which is this dark one, you will realize that every moment, at every point, one wave is at crest and the other one is at trough. Notice that this is the wavefront of the source 1. Okay, and this is the wavefront at this location, at exact this point. This is the wavefront of the second source. Although these lines are actually representing crest and crest, but the empty space between them is actually trough. So if you carry that at this point, you realize that one of the wave has a trough and one of the wave has a crest. Because of this, this region is experiencing destructive interference. And of course, this can be extended to all the areas on the screen. So this is what scientists observe on the screen, but this is not what they were expecting. They were expecting that they will only see right in front of these sources, they will only observe only two images, only two light sources, or only two spots of light. But they saw a pattern of dark and bright fringes, which actually gave them the guarantee that yes, light is diffracting, If it is coming in parallel wavefronts, for example, if it is coming like this, after passing through these holes, it's becoming circular. This is what this experiment actually guaranteed. Okay, first guarantee, first finding by this experiment. And on the other hand, they were actually looking out to find out the wavelength of light, which they could not have done at the time because they didn't know how to do that. So what they did was they created this experiment, and then they took these measurements and find out a ratio. There is a mathematical proof for that. That's not a part of the course. So let's say that this gap is A. Let's say this gap is D. And the distance between the fringes, these are called fringes, by the way. These are fringes. So if this is a region, we will call this a fringe. This is also a fringe, but this is a bright one, this is a bright one, and this is a dark fringe. And we know it's bright because of constructive interference, dark is because of destructive interference. So the separation between them from bright to the next bright is called X. Or if you want to choose from dark to dark, this will also be called X. Both are considered to be X. So it's your choice. You want to choose dark to dark or bright to bright, they will still give you the same answer. So X was defined as the distance between two successive bright fringes on the screen, or it was defined as distance between two successive dark fringes, because it will be the same. So the formula, the ratio that they actually landed was AX equals to lambda D. Now the lambda is actually the wavelength that is being introduced in the double-slit experiment situation. We don't know that because now we know that what that wavelength is. We know that the visible light is in the range of nanometers. We could not have seen that with the eyes, right? And we certainly didn't have the experiment or the apparatus that we have today, electron microscopes and the attosecond lithography. We don't have that. We have that right now, but we didn't have that at the time. So they wanted to find out the wavelength of light. And of course, leading from, because light could be seen, that's why they started the experiment with that. But then they measured for everything from gamma up to radio waves. That is how they measured it. So what happened at this situation? So they make lambda the subject of the formula, and they land at this equation, which is AX over lambda D. Now, what do we do with this? What is the purpose of this equation? So what happened was that this A is generally in the range of millimeters. X is also generally in the range of millimeters. And D is generally in the range of centimeters to meters. All these measurements that I've just highlighted can be measured with the ruler. They could have done that. So they did exactly that. So they placed a ruler at this point, they placed a ruler at this point, they placed a ruler at this point and measured everything. Now, since everything is measurable with a ruler, micrometer, vernier caliper, they placed those quantities over here and performed the arithmetic operation and found the wavelength of all the electromagnetic spectrum going from gamma moving to radio. This is the main, you can say, purpose of this double slit experiment. It gave you two ideas. The first one was that the light is diffracting. Otherwise, we could not have known that. Second, it helped us to calculate the wavelength of light. That violet starts from 400 nanometers, violet or indigo, and goes up to red, which is 700 nanometers. I hope that the purpose of this experiment is clear now. Why did we do that exactly? Okay. And most definitely, it has the role of interference. It has the role of constructive interference, destructive interference, which I've already covered in part 6 and part 5. Okay. So please don't forget to watch them to fully understand what is the addition of the waves. Then we move towards the difference, this path difference. Now, the problem with this experiment or the problem with this situation is that we can't visualize this again and again. We can't run this animation for everyone at all times to fully understand where there's going to be constructive interference and where there's going to be destructive interference. So instead, what we've done is devised a method to predict whether this is going to be constructive or destructive depending upon the situation. And that method is known as path difference, the path difference method. Now, we have seen this diagram over here in this animation. This is actually a completed version of that we have two sources, source 1 and source 2. And wherever the crests are meeting crests, there is a constructive interference. Wherever they are not, there is a destructive interference zone. Now, how do you do that at all times? How to do that? So it's a very simple method. What they do is they actually find the distance in comparison to the wavelength. Now, over here, if you analyze at the very last section, both waves are actually producing their crests. So if both of them had an amplitude of A, the resulting would have an amplitude of 2A. This is constructive interference. And let's involve signs into them, because this is a negative displacement. So negative A added together will be negative 2A. It will be an addition of the waves. Since the waves are still being added together, the waves have not been destroyed completely. That means this is going to be a constructive interference, right? Okay, let's move towards the other idea. What happens at the destructive interference? Why there is a dark band? Why there is dark light at this situation where there is no light? What's happening at this point? So light from both sources, let me draw from this area. Light from both sources is actually moving like this. Now notice that when it reaches this point, this wave is at crest. It has a crest when it reaches that point. It is possible that when the light reaches from this source, it actually makes a trough. In the last section of their lifetime, one has a crest and the other one has a trough. That's why they're going to destroy each other and make a destructive interference or dark band at this point. Now, again, it brings me back to this point. We can't do this again and again. We can't make these waves again and again. So what we've done, we've devised this method. Let's try to understand what that is. So path difference is simply the distance or the difference of distance. How far is that point from the source? Difference of distance, but in reference or in light with the wavelength. Okay, so a general shortcut is that if you get an integer because of the path difference, let's say 0 lambda, 1 lambda, 2 lambda, 3 lambda, that means it's going to be constructive interference. This is constructive interference. For destructive interference, you will get a multiple of 0.5 lambda. You will get a number of 0.5. So 0.5, 1.5, 2.5, 3.5 will be your destructive interference. Now be advised, it has to be 0.5. It has to be 0.5. Why? Because we know that at the end of the journey, only half of the wavelength can be displaced, or it can be different from one another. You see, if this completes its wave like this, then this is actually like this. So this is 1.5 lambda, the one that I've colored actually. And in the last section of its life, this one actually makes a complete one wavelength. So when you take the difference of wavelengths, you'll realize that this is actually 0.5 lambda different, which is mentioned in this situation as well. Lambda by 2, there is a difference of half a wavelength. This half a wavelength at the end of its life is actually translating like this, that the point of meeting, one of the source is actually coming like this, let's say, and one of the wave is actually coming like this. So I can see that the red one has a crest and the blue one has a trough. They will destroy each other because they're opposite to one another. Their answer will be 0. So to find this difference of exactly 0.5 lambda is important. Notice that in some questions that I'm going to solve in this video, you'll realize that in some situations the path difference will come out as 0.3, 0.2, 0.1. That is still constructive interference. For complete destruction, we need 0.5 factor. Okay, so what is the phase difference in these locations? So let's go towards this animation again, and let's run it again. So this is what's happening at this point. Okay, let's move it a bit back. Okay, at this point. So what's happening and what are the phase differences at these locations? What's going to be the path difference at this location? So I'm going to teach you a simple shortcut for this. First, I'm going to write down the path differences, and then I'm going to write down the phase differences. Be advised that this is going to be a methodic way of doing this. So the center one is going to have a path difference of 0 lambda and a phase difference of 0 degrees. Because waves from both sources, when they come to this point, they have no difference among them, and they create a constructive interference pattern at this point. But as you move down, as you move up, you realize that you've encountered the first destructive interference. Over here, the path difference at this point will be 0.5 lambda. As I've mentioned you before, that the destructive interference needs to have a factor of 0.5. Then the next bright fringe where the constructive interference taking place will be actually a difference of 1 lambda. Now you've figured out the pattern. This will be 1.5 lambda. This will be 2 lambda, and this will be 2.5 lambda. Similarly, when you go down from the 0 reference, the first dark band is going to be 0.5 lambda. This will be 1 lambda, 1.5 lambda, then 2 lambda, and then 2.5 lambda. So constructive interferences have whole numbers. They have integers. Destructive interferences have 0.5 factor, nothing else, nothing other than 0.5 factor. Please be advised. Now let's count the phase difference. So for the 0.5 factor, it will be 180 degrees. For the first constructive interference, this will be 360. And for the 2 lambda, this is actually going to be a times 2 factor. So this is going to become 360 multiplied by 2, which is 720 degrees. And of course, for the third one, it would have been a multiple of 3. Okay. Now, when you go to the next destructive interference, just simply add 360 into this 180, and you realize that after adding that, you get 540. So this is going to be a phase difference of 540 degrees. Again, add 360 into this, and you will get the next one. That will be 900 degrees. Right? What some students will find in the books is that not only this is represented in degrees, this is also represented in radians. So this is going to be 0 pi radians. Okay. This one will be actually, since this is 180, so this will be pi radians. This one will be 2 pi, as 360, of course, which is represented at this point. And this one will be actually 3 pi. So you can multiply this with the 3. Just a moment. So 180 multiplied by 3, you get 540, which is what you get at this point, at exactly 1.5, right? So at 2 pi, you'll get 4 pi, and at this one, you'll get 5 pi. So 5 multiplied by 180 gives you 900, which is at this location. So you can either find your answers in the form of pi, or you can either form your answer in the form of degrees. I hope that we understand what's the shortcut about this question, because this is going to be very helpful for us when we move towards the questions. Okay. All right. And it's very simple to understand. Let me pause this video and bring it back to the original position. I just mentioned at this point that let's say this is going to be, let's write this down again. This is 0 lambda. This is 1 lambda. This is 2 lambda. So what is this lambda? What's actually happening? So let's make that source. So from this source, let's say that we are getting a crest at this point. From the second source, when it moves, we will also get a crest. Okay, but the difference of path is 1 lambda, which means that this wave, let's say for the sake of example, may have covered 3 complete wavelengths to come there. And the other source may have completed 4 wavelengths to come there. So the difference between them has been of 1 complete wave. So 1 complete extra wave has been covered from this source too, because it is further away from this point. It has to travel a longer distance. So how much longer has it had to travel? It had to travel at least 1 more wavelength. And when they move at 2 lambda, that means that from source 2, it has to travel a longer distance. It had to travel a longer distance of at least 2 more lambdas as compared to the wave from source 1. This is path difference. It helps us to understand, it helps us to quickly guess whether this is constructive or destructive interference. So with integers, if we write down the phase differences, for example, then this will be 0 degrees. This will be 360. Okay. This will be 720. And of course, this will be 3 times the 360 degrees, right? So this will be 6 pi. Over here, we can find out that this is going to be pi. This is going to be 3 pi. This is going to be 5 pi. This is going to be 7 pi. So you can develop a ratio for them, for yourself.